Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at topical past paper questions for paper 1 on the topic of waves for Cambridge A-level physics. Now, these topical questions come from the Papa Cambridge website, which I will leave a link to in the description below, and you can use these questions to prepare for your paper 1 exam in Cambridge A-level physics, and you can study for for this paper topic by topic by using these topical past paper questions. Today we're just going to look at questions 721 to 731 on the topic of waves. And the topic of waves is not an extensive topic, but it is a very important one. And it leads on to superposition, which is technically still a topic on waves. But we're just going to deal with the waves part for this video. And then in a later video, we'll deal with the superposition of waves, that is. Now, the first question is 721. It comes from the March 2020 exam. It's question paper 1, variant 2, and it's question 21 from the paper. We are told that a wave of frequency 15 Hertz travels at 24 meters per second through a medium, and we want to know the phase difference between 2 points that are 2 meters apart. So, well, let's look at the wave equation, shall we? We know that the wave equation V is equal to F lambda, meaning I can find the wavelength of this wave. Lambda is the speed of the wave v divided by the frequency f, which is 24 meters per second, which is given, divided by the frequency 15 hertz. This gives us a wavelength of 1.6 meters. But 2 points in this wave are separated by 2 meters, so we want to know by how much their phase differs. So if I just roughly sketch what this wave would look like, if I just roughly sketch this wave and then I draw the equilibrium position to the center, when we get to the first crest, that will be 0.4 meters. And when the graph, so imagine this is displacement versus time, then at 0.8 meters, the graph cuts through the horizontal axis. And then the first trough is at 1.2 meters. And then a wavelength is 1.6 meters, which we calculated. So that distance is one wavelength. And then 2 meters would be at the next crest. And what we can see here is that the difference in wavelength between 1.6 and 2 is a quarter. So that's a quarter of a wavelength out of phase. So the phase difference for a point that starts at the origin, as we can see, will be quarter a wavelength out of phase. And how we can calculate this would be to take the distance between the points minus the wavelength. So you want to basically find the difference in the path between the points, the path length, divided by the wavelength. So as a fraction of the wavelength, what's that path difference? And what we find is that 1/4 of a cycle. So if we wanted this in degrees, we would multiply this by 360, or in radians by 2 pi, and we get a quarter times 2 pi, a quarter times 360 degrees. So in terms of a full wavelength, it's a quarter of a wavelength out of phase, and this is option B. So always look to compare the difference in the position that we are taking into consideration and the wavelength, and calculate that as a fraction of the wavelength. And then you can calculate the phase difference in terms of pi or in terms of degrees. Now, question 722 says a sound wave. Again, this question is from summer 2020. That's May-June 2020. It's from question paper 1, variant 1. And it's question 22 from the paper. It says that a sound wave reduces in intensity but maintains a constant frequency as it travels through air, and we want to know which of the statements are correct. So its intensity is dropping, but its frequency remains the same. Remember, frequency is related to wavelength. 1/frequency equals wavelength. So if I were to sketch a graph of displacement against time, what would this graph look like? Let's call the displacement x. Doesn't really matter. And then the time axis is the horizontal axis. Now, the intensity of a wave we know is proportional to the square of the amplitude. So the intensity going down means the amplitude is dropping with time, but the frequency is remaining the same, meaning the wavelength is remaining the same. So essentially what we have is a decaying sine function where every subsequent crest is smaller, every subsequent trough is smaller, and eventually the wave will just have a zero amplitude. Okay, and so we still have a constant frequency and a constant period, but we have differing amplitudes, and because we have differing intensities. And so we want to know which of these statements are correct. Is it that the maximum displacement of the particle changes between one particle and the next? The phase difference between adjacent particles is zero. The wavelength is the distance between two particles that have a phase difference of 180 degrees, and two particles that have a phase difference of 360 degrees have the same maximum displacement. Well, here's a particle at this point in time. I'll call it particle A on the wave. It has a much higher amplitude than a particle that is in phase with it, but some distance along from it. So particle B has a much lower amplitude, so its displacement is less. So immediately we can see that the correct answer is A. But we can also eliminate B, C, and D. I mean, the phase difference between two adjacent particles will never be zero for any wave. The wavelength is the distance between two particles that have a phase difference of 180 degrees will also never be true, because the wavelength is the distance between two particles that are out of phase by 360 degrees, or 0 degrees, or any multiple of 360 degrees. And lastly, two particles that have a phase difference of 360 degrees have the same maximum displacement. They can't have the same maximum displacement because that would mean the intensity is constant throughout. So the correct answer here for 722 is option A. The maximum displacement of particles changes between one particle and the next. You can see particle A has a greater displacement than B, has a greater amplitude than B, and then any other particle further on in time would have an even lower maximum displacement, an even lower amplitude. The next question is 723. It's from the summer 2020 exam. It's question paper 1, variant 1, and it's question 23 from that paper. Now, the graph that we are shown gives us the variation with time of the displacement of an electromagnetic wave at a point, where the displacement is measured in some arbitrary units and the time in microseconds. The wave is traveling in vacuum, and we want to find the amplitude and the wavelength of the wave. So it's a common question, common in paper 1, that you get questions that ask you to calculate two things, even though there's only one correct option. That's because there's a row that is the correct row. So the first thing I'm going to do for this is calculate the wavelength of this electromagnetic wave. We must remember that this wave is an electromagnetic wave. And so actually we calculate the amplitude and then calculate the period. So the displacement means I can find the amplitude, but I don't know the unit. So the displacement, the amplitude of the displacement will be 3 minus 0. So going from 3 to the horizontal axis, 3 minus 0 is simply 3, and it's arbitrary units. So I'm just going to label it AU for arbitrary units because I'm too lazy to write down arbitrary units. So that's the amplitude. The period of this wave is the time. On the time axis, I'm reading, well, crest to crest or peak to peak or point in phase to subsequent point in phase. I've just chosen crest to crest. Doesn't really matter. The period will be the same. And this is 30 minus 10. So I've chosen those 2 points. That's one wavelength, crest to following crest. And this is 20, but I must be careful. The units are microseconds. But the options ask us for amplitude and wavelength, not amplitude and period. So I have to figure out how I'm going to get the wavelength from the period. Now the wave equation for an electromagnetic wave is C is equal to F lambda, C being the speed of light or the speed of an electromagnetic wave in vacuum. I can also write the frequency as 1 over the period, so I can write C as lambda over the period t, which means then that the wavelength lambda is C times t. Remember, this is an electromagnetic wave, so its speed is 3 times 10 to the power 8 meters per second. and the period is 20 microseconds, or 20 times 10 to the minus 6 seconds. And this will give us a wavelength of 6,000 meters. And the wavelength in our table is also measured in meters. So I'm looking at option A, an amplitude of 3 arbitrary units and a wavelength of 6,000 meters, which corresponds to option A. So a nice question that made sure we understood that we were looking at an electromagnetic wave before we chose a suitable number for the speed of the wave. Question 724 is from the summer 2020 exam. It's question paper 1, variant 2, and it's question 22 from that paper. Two progressive waves meet at a fixed point P. The variation with time of the displacement of each wave at point P is shown in the graph, and we want to find the phase difference between two waves at point P. So these are two waves that are overlapping at the same point in time, and I want to find the phase difference between them. So how do I find the phase difference between two waves? Remember, these two waves must be coherent. They must be from the same source, or at least must have the same frequency. Now the phase difference is the change in the difference in time between the period. Now the period will be the same for both waves. It's the only way we can discuss the phase the phase difference between two waves is if they have the same frequency and hence the same period. So it's a difference in time divided by the period. And when I say difference in time, I mean it's the difference in time between 2 points that are in phase, 2 points that have the same phase. And so we take that number and we multiply it by 360 degrees because that's the angular frequency for a full cycle. And what I'm going to take are two arbitrary values of time, 0.6 seconds minus 0.3 seconds, those 2 points being in phase, because those are subsequent troughs. So 0.6 seconds is the trough for the bigger wave, the one with the higher amplitude, and 0.3 seconds is the trough for the smaller wave that is following just behind it. So let's assume that the bigger wave is slightly ahead and the next wave's trough takes 0.3 seconds to catch up, 0.3 seconds behind at that moment in time. And the period for both the waves are the same, and I can see the period is 0.8 seconds. You can calculate this from either of the waves. And then I multiply this by 360 degrees, so I get this as a fraction of a wave, and I find this phase difference to be 135 degrees. So the two waves are out of phase by 135 degrees. So they're neither constructive interference nor are they destructive, but something in between. And this corresponds with option C. So not too bad, but that's how you would find the phase difference between two waves that are sort of overlapped on the same axis. Look for the difference in time between two successive points in phase, or two successive crests or troughs, and then compare that with the wavelength of the two waves and multiply it by 360 if you're using degrees, or 2 pi if you're using radians. Now question 725 is from summer 2020. It's question paper 1, variant 3, and it's question 22 from that paper. We are told that a wave of amplitude A has an intensity I. After passing through a certain medium, the wave has a new intensity of I over 4. What is the new amplitude of the wave? Okay, so the first thing we remember is that the intensity of a wave is proportional to the square of its amplitude. Square of its amplitude being important. We don't actually know the equation, we just know that this is the relation in A-level physics. Square of the amplitude. This means that the amplitude of a wave is proportional to the square root of the intensity. I'm just flipping this equation around. That means whatever the new amplitude is, if I divide it by the old amplitude, what I must get is that this will be equal to the square root of the new intensity over the old intensity. How do I know that this the proportionality becomes an equation? It's because I'm dividing a new by an old, so whatever constants are included in the proportionality to make it an equation will cancel out anyway. And so that means the new amplitude will be the old amplitude, a little bit of mathematics here, times the square root of the ratio of the new intensity to the old intensity. Again, you don't need this many steps in your answer, but I'm just showing you the first principle way to get this answer. And the initial intensity was A. We multiply this by the square root of I over 4I. So the new intensity is I, but the old intensity is, or rather the new intensity is 1 over 4I and the old intensity was I. So when we do this calculation, we see the i's cancel as they should, and we get a new amplitude that's half the old amplitude. So A over 2, and this corresponds with option B. So whenever you're dealing with questions that have amplitude and intensity in it, you have to remember the relationship that intensity is proportional to amplitude squared, and be able to rearrange that to say amplitude is proportional to the square root of intensity when needed. Question 726 is from the March 2019 exam. It's from question paper 1, variant 2, and it's question 1 from that paper. We're told that a wave has a frequency of 5 gigahertz, and we want to find the period of this wave. Well, probably could do this in your sleep. Period is 1 over frequency, which is 1 over, now gigahertz is, 1 gigahertz is 1 times 10 to the power 9 hertz. So 5 gigahertz is 5 times 10 to the power 9 hertz. And then the rest is just putting this into your calculator. This is 2 times 10 to the minus 10 seconds. This is more a question on, do you know how to convert between the different prefixes? So 2 times 10 to the minus 10 seconds is not on the list of options. But I can write this as 200 times 10 to the minus 12 seconds. Now, why would I do that? Because 10 to the minus 12 is a special prefix. It's a picosecond. And so I can replace the 10 to the minus 12 with the small letter p. And so I get 200 picoseconds, which is option A. That's more of a, can you change between different prefixes? Do you know how the prefixes work? Rather than a really difficult question on waves. But you did need to know the relationship between period and frequency in order to solve that. The next question is 727. It comes from the March 2019 exam, question paper 1, variant 2, and it's question 23 from the paper. We are told that the top row of bars represents a set of particles inside the Earth and at rest. The lower row represents the same particles at one instant as a longitudinal wave passes from left to right through the Earth. What should be measured to determine the amplitude of the oscillations of the particles in the lower row as the wave passes? Is it half the maximum displacement of the particles from their rest position, half the maximum distance apart of the particles, the maximum displacement of the particles from their position at rest, or the maximum distance apart from the particles? Now, this is a bit of a confusing one, but if you remember, by definition, if I have a particle, take a single particle in a wave and I look at its oscillation, it could be a sound wave as well, then the amplitude of oscillation is the distance from rest position to maximum displacement, right? So that's the amplitude, the distance from rest position to their furthest point, the maximum distance of the particles away from the origin. But it's a vector. So we can't simply say distance because it doesn't really tell us unless we specifically say direction. But if you remember your definition of amplitude, what is amplitude? Amplitude is maximum displacement from rest. I'm going to write it down so that you remember, but you should remember that amplitude by definition is the maximum displacement of a particle from the rest position. So I don't really need to think about this picture or think about the actual scenario because the answer is the definition. The maximum displacement from rest of a particle is its amplitude, and so that's option C. So we didn't have to sort of try and understand the entire picture or the entire scenario, but we do need to know that definition of amplitude as a quantity. Okay, the next question is 728. It comes from the summer 2019 exam. It's question paper 1, variant 1, and it's question 27 from that paper. We are told that two progressive waves of frequency 300 Hz superposed to produce a stationary wave in which adjacent nodes are 1.5 meters apart, and we want to know the speed of the progressive waves. So this is actually more of a question on superposition, but it's fine, we'll answer it anyway. Now, what do we know about a standing wave is that the separation between the nodes, I'm going to call them delta nodes, the separation between the nodes is two successive nodes is half a wavelength, lambda over 2. That means the wavelength of a wave is 2 times the separation between the nodes, which we are told is 1.5 meters. So that's 2 times 1.5. And this means that the wavelength of the wave is 3 meters. So we found the wavelength of the wave, but we need to find the speed of the wave. Okay, and let's draw this actually. Let's just see what this looks like. So I have one wave superposing with another wave. And the separation between nodes, the nodes being the points of zero displacement, was 1.5 meters. And we can see that that's lambda over 2. That's half a wavelength. That's how I got the wavelength to be 3 meters. The wavelength should be the entire distance between two successive nodes and then the next two successive nodes. Okay, so now that I have the wavelength of the wave, finding the speed should not be too difficult. Speed, using the wave equation, v is f times lambda. The frequency is given as 300 Hz. The wavelength is 3 meters. So the speed of the wave is 900 meters per second. And this corresponds with option D. So it's not necessarily difficult when we have to apply the wave equation, but knowing what to put in the wave equation can be tricky, especially when it's superposition and you need to understand how to find the wavelength if I know the position of specific nodes or antinodes in the standing wave. So that was more of a question on superposition, but it's fine. We study waves in superposition and we study them together usually, like we should. The next question is number 729. It's from the summer 2019 exam. It's from question paper 1, variant 2, and it's question 23 from that paper. Now we are shown a diagram that illustrates the position of particles in a progressive sound wave at one instant in time. The speed of the wave is v, and p and q are 2 points in the wave that are distance l apart. We want to know an expression for the frequency of this wave. Okay, a little bit complicated. Let's draw. Well, we don't really need to redraw this diagram. Since it's drawn for us, I can just write on the diagram itself. But let's assume that point P is a crest. So there's a crest of the wave, and I'm thinking if I'm looking at this wave from above, that's the crest of the wave. And then as the waves move apart, I have a trough at point Q. And then the subsequent part that looks exactly like P, the next point in phase will be where the particles all join up again, and I have another crest. So what do I know? I know that the distance between crest and crest is one wavelength. So if I were to maybe draw an arrow from, actually, let's draw it from the equivalent of point P on the other side. What I would have is crest to subsequent crest is a distance, which is the wavelength. It's equal to lambda. So what I can see is that, and well, P and R are in phase here. P and R, I'll call this point R, where I've drawn the dot. P and R are in phase, and there are subsequent points in phase, hence the distance between them is one wavelength. And how do I know they're in phase? Because the particles are doing the same thing at the same time. They're all bunched together. And I'm looking at the middle particle specifically at P and then again at R. And what I can see is that the wavelength lambda is twice the distance between P and Q. L plus another L, which is 2L. And the frequency of a wave is its speed divided by its wavelength. From the wave equation, V is equal to F lambda. But lambda is 2L, so the frequency of the wave is the speed V divided by twice the length. And this corresponds to option A, V over 2L. So in this kind of question, you must identify crests, troughs, or points that are in phase. Look for 2 points that are subsequently in phase, 2 points in phase that are next to each other. And from there, you can then figure out what distance they are apart, and then you can derive an expression for the frequency or the wavelength or the speed or whatever you need. Okay, so that was an interesting question. The next question is 730. It's from the summer 2019 exam. It's question paper 1, variant 2, and it's question 24 from that paper. We're told that a wave moves along the surface of the water. The diagram shows that the variation of displacement S with the distance along the wave at time t is equal to 0. And we want to know which graph best shows the variation with time t of the displacement S of the point P on the wave. Okay, so we have a graph of displacement against distance, and we want to know what the displacement against time graph is going to look like. So let's outline some key features of this graph. Now, the first graph is displacement versus distance at a snapshot in time. When t is equal to 0, we take a picture of the graph from side on, and that's what we see. Point P is above the horizontal. If it was a water wave, it's above the surface of the water, above the equilibrium position of the water, and the wave is moving to the right. So we watch the wave moving to the right towards the shore. If it was an ocean, a water wave in the ocean, for example. But what I can see is that at time t equals to 0, this displacement of the particle at P, or the point P, is positive. So when t is equal to 0, the displacement is greater than 0. That's an important thing because that's going to tell us how to choose our graph from the 4 options. And then at some later time, I don't know what to call it, so I'm going to say at time t is equal to t1. So some short moment of time after t is equal to 0. And I'm going to say small time t1, not too long after. I'll take another snapshot. What's going to happen? Well, if I'm looking at displacement against distance, then the wave will obviously move to the right because I'm told that the wave is traveling, the direction of travel is left to right. I'm given the direction of travel of the wave. So if I were to sketch a graph of displacement against distance for this later time t1, not for time t, what I would find I'm just going to plot a graph of displacement against distance. The wave is now moved to the right. So if it moves to the right and point P is at least along a vertical at the same place, then the the wave has moved to the right, and point P is now higher up than it was before. So point P is now higher, has a greater displacement than it does before. So it has S being greater, because think about this wave moving to the right. As this wave moves to the right, the crest has still to reach point P. But at a time t1, just after t is equal to 0, the crest catches up, finds point P, and pushes, obviously, point P to the amplitude. And so if P is at a higher position, it has a greater displacement. So why is this important? Well, because I now need to decide what the displacement versus time graph looks like? Well, initially the displacement is positive, so I have to look for a graph where the displacement is initially positive. And that's option A and option D. But then I must look for a graph that has a displacement that is greater than its initial displacement. And so the displacement is going to increase with the time t1. So at time t is equal to 0, I have a positive value, and the displacement increases after a short time t1 has passed. And so that corresponds with option D, where the displacement is greater than 0 initially, and then gets even greater as the wave moves to the right a short time later. And so that corresponds with option D. So the direction of travel of this wave was very important. And the displacement must increases, but if we look at A, the displacement is decreasing with time. So a little time t1, the displacement of P would be less than it was. So it has to be option D. Now, the last question we'll do in this video is 731. We'll ignore 732 for now. So 731 is from summer 2019. It's question paper 1, variant 3, and it's question 21 from that paper. We're told that the graph is showing the variation of displacement y with the distance x along a progressive wave at one instant in time. And we want to know the phase difference between points P and Q on the wave. Now remember, we've done phase difference before. So how do you do the phase difference? Well, look at those 2 points. And let's find the difference or the separation or the difference between these 2 points as a fraction of the wavelength. And we want to answer in degrees, so we multiply it by 1 cycle, 360 degrees. So if I look at the graph going from P to Q, I can see that one complete wavelength would be from P is a trough, so the next trough would be one complete wavelength. But let's say I'm going all the way to Q now. Then I'm going from trough to subsequent crest. And so that distance is half a wavelength, lambda over 2. I'm going halfway to the next trough. And so what this means is that my path difference between these 2 points is 1.5 wavelengths, half plus 1. And so that's 3 over 2 lambda divided by lambda multiplied by 360. The lambdas cancel, and what I'm left with is 1.5 times 360. And so the phase difference is 540 degrees. So we go from point P, we change phase by 540 degrees, and we reach point Q on the wave. And that corresponds to option C. So you can see that when we have to calculate phase difference, we need to know what the path difference between those 2 points on the wave are, or between those 2 points on 2 different waves that are placed on top of each other. And then we can figure out what the phase difference is by multiplying it by 2 pi or 360 degrees. And in this case, we get 540 degrees. So I hope this video has been helpful. You can see that the topic of waves is not overly complicated, but it will become a little bit more or a lot more complicated when we do superposition, depending on how you look at it. But if this video was helpful, then please leave a like, leave a comment down below, subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.